and we're going to have different mechanistic pathways, whether they're strong or weak nucleophiles. So figuring this out has to do with things like noticing if they're charged or not, thinking about the electronegativity of the element, how easy it is to give up electrons, and things like that. So our learning objectives are all dealing with topics in chapter 17. So we're going to continue to think a lot about the element oxygen, whether it's in an ether, whether it's or in an epoxide. One thing that I've dropped a methyl group at the very end of last time's lecture. So I want to go back to that example here. So on the very last thing that you wrote down, I dropped this particular methyl group. And so I'd really like everyone to make that correction in their notes so you don't get confused. So just add one methyl group to your carbon count there. Originally when I posted it, I did not have that there. So please go ahead and make that correction in your own notes so that you do not get it wrong. So again, this is the very last thing that we talked about. And thank you to the student that pointed this out. All right, so now that you've done that, let's go ahead and get into the content for today. All right, so we're going to learn more about epoxide chemistry. So we've been thinking a little bit about epoxide chemistry and learning how to make these, learning how to open some of them with ethylene oxide. And now we're thinking about specifically the type of nucleophile that we're going to use. So learning objective 17J is going to be the 4 Ps for epoxide ring opening, specifically with strong nucleophiles. And you can find this in chapter 17.11. All right, so we need to start thinking about what is a strong nucleophile. So we can think of something like an organometallic reagent would be a strong nucleophile. All right, so strong nucleophiles, we'll start a list here. All right, so we can think about things like organometallics. All right, and so if we have an organometallic and we have, for example, an epoxide that does have some stereochemistry associated with it, right? This here is a stereocenter. Oftentimes we put a little asterisk by stereocenter so that we can indicate that we see them there. We know that organometallic reagents, we need to worry about things like acid sensitivity. So this is going to be step 1. We're just going to have our organometallic reagent, and then at the end of the day, we're going to have a step 2, and this is our H3O plus workup. Right, because at the end of the day, we're not going to just get we would get an alkoxide out, and we'd really like to protonate that. So this is just an SN2 reaction. When we're considering SN2 reactions, we're always thinking about sterics, or we should be. And so we can take the electron density from the R magnesium bond, and we can go ahead and have that attack the less hindered position. And then when we do that, we break a carbon-oxygen bond and return those electrons back to our oxygen. All right, so this is just an SN2 reaction. Our leaving group in this case, it's part of this 3-membered ring, this epoxide ring, so it doesn't leave and float off into the ether, but instead it's still bound to our molecule. So we have gone with the less hindered position. Right, because it's SN2. We always are trying to think mechanistically. Okay, so the product of this reaction then is going to be, we're not going to change our stereocenter. We really haven't reacted at that position. We would have our H3O plus workup, so we'd protonate from that, and then we would have our R group that's now bound. All right, so that's the bond that we've made, and the H3O plus workup is how we protonate. So note here, right, this stereocenter that we had here does not change. right? Nothing changes there, right? We haven't reacted at that position. We're not doing any sort of inversion of stereochemistry or anything like that. Okay, let's talk more about this nucleophile. So our organometallic reagents work. We can also use cyanide, all right? We can use azide, which is N3 minus. It has a lone pair of electrons. It's negatively charged on a nitrogen, pretty nucleophilic element. Great. We can use deprotonated alkoxides, OR minus. We can use sulfur nucleophiles, thiolates, S minus. We could even use our old reagent, lithium aluminum hydride, right? Because here we're talking about H minus effectively. I'll put that in quotation marks, H minus. Right, so these are all really strong nucleophiles. We see they're anionic. We see that, you know, they have the ability to, they're not very hindered. They only have, for the most part, one group attached to the nucleophile that's attacking. All right, so another example, for example, we could use, let's use methyl sulfide as a the thiolate. So we always have to have a counter ion. Let's just arbitrarily say it's going to be sodium. You could have potassium, doesn't matter. Let's take epoxide in this case. Let's have something that has a CHEM dimethyl group. CHEM means geminal on the same carbon. So let's see, that SN2 reaction would be at play. We just take our strong nucleophile, would attack at this carbon to break a carbon-oxygen bond. Our intermediate there, before I haven't added the H3O plus yet, is going to be have a methyl sulfide that's now bound in the sodium plus counter ion. And then, of course, we know we need to add H3O plus. We can go ahead and we can protonate that alkoxide to give us our alcohol. This workup just allows us to have a neutral species that's now an alcohol. All right, same mechanism for azides, for cyanide, alkoxides, doesn't matter. This is our sort of list of strong nucleophiles, right? And this H3O plus we know is our second step, right, in our reaction, because we can't have a strong nucleophile, not just a Grignard or an organometallic reagent, but methyl sulfide would also be able to deprotonate H3O plus. It would form the thiol, which is not nucleophilic enough for this type of chemistry. Okay, so at this moment in time, we have just dealt with reacting at a carbon that doesn't have other substitution. There's no stereocenter involved. Okay, so what happens when we do bring in stereochemistry? So let's take a look at an example where we might have an epoxide that looks like this. We have our two wedges indicating that the oxygen is coming out of the plane of the board. Say we wanted to add sodium cyanide to this. That would be our good nucleophile. So our CN minus is a lone pair on it. Sodium plus counter ion. Again, this is just going to be an SN2 reaction, but we need to think about what happens to our stereocenter. So these carbons are equivalent. We could attack either one of them. I'm just going to draw the arrows for one of them first. So we have this lone pair of electrons that's going to go ahead and attack that carbon-oxygen bond. The carbon-oxygen bond is going to break. It's going to put a lone pair of electrons on our alkoxide. So now we have the situation. The stereochemistry of the leaving group is not changing. Right? We still have a minus there. We can bring through our sodium counter ion, sodium plus. But we've inverted this stereocenter when we add our cyanide there, right? And this is an SN2 reaction. So Inversion of stereochemistry. All right. If we were to use a different a set of arrows and draw a nucleophilic attack at the other carbon that's bound to the oxygen here, try it on your own, you're going to get that inverted as well. This is a inversion of stereochemistry, so it depends, again, as we talked about last time, if this is a one-to-one mixture of your epoxide, the R and the S, or if this is going to be just one enantiomer, then it would turn out to be one enantiomer in the product. We're not commenting on enantioselectivity, we're just commenting on this relative stereochemistry that this has inverted. All right, let's go ahead and bring it home and add step 2, which is our H3O plus. And we know that our alkoxide is pretty basic, so it's going to go ahead and deprotonate to generate our neutral species. No stereochemistry has changed in this case. All right, so we see that these stereocenters have not changed from the deprotonation of H3O plus. Right? So we always need to be thinking about stereochemistry. All right, so let's do a practice problem and let's see if we can think about the 2 scenarios where we do need to deal with stereochemistry or we don't need to deal with stereochemistry. So if on an exam, what you saw was this problem with this ethyl substituted epoxide, and your nucleophile that's listed first is sodium methoxide, for example. And the reagent arrow said H3O plus. We would need to predict the product with the correct stereochemistry. So go ahead and take a few seconds to see what you would get. All right, so if I was you, I would evaluate the mechanism that this operates under. This is an SN2 mechanism. So I would be thinking to myself, SN2 mechanism does invert stereochemistry at a stereocenter, but I would be thinking, is there stereochemistry at the carbon that I'm going to react at? So we have 2 options, right? We could react at this carbon, or we could react at that carbon. And I would say an SN2 mechanism is most favorable at the less substituted carbon. And so that's where I would have my nucleophile react. So that means that my product, at the end of the day, would have the same stereochemistry of this ethyl group, because we don't need to worry about inverting it because we're not attacking at that particular stereochemistry, right? So the stereocenter here is not touched. Because the SN2 mechanism says I should choose the less substituted carbon. All right. So can we ever change this? Can we ever get a reaction? Say you didn't want this product. Say you wanted the products at the more substituted carbon. Is there a way to get that? Well, chemists are pretty clever, and we often take a look at what the needs of the community are in terms of what types of molecules people need to make medicines or agrochemicals and things like that. And then we develop methods to overcome this. So that's our next learning objective. It's going to be learning objective 17K. And this is the 4 P's for the acid catalyzed. So remember before we had strong nucleophiles that were deprotonated. Now we're introducing acid into the reactions. We're not dealing with that. So this is the acid catalyzed ring opening of tri-substituted epoxides. Right, and this is in 17.12. I'll add the caveat that the book is not 100% correct here. Right? Maybe it blows your mind that the book isn't 100% correct, but Professor Lamb did her PhD in epoxide ring opening, which is this very reaction. She's one of the world's experts on this reaction. And so, we talked about it, and the book kind of oversimplifies some things. And so we're just going to pay attention to what's in the class notes, all right? Even though the book has some cases that it makes out to be very clear cut, but actually are not the most clear cut, all right? So we're just going to deal with these tri-substituted epoxides only, okay? Tri-substituted, because those are pretty clear cut. Okay, so let's kind of take a look at what the scenario is going to look like. A tri-substituted epoxide means we're substituted with 3 things. Right, our oxygen has 2 bonds to it, meaning it also has 2 lone pairs of electrons. So our learning objective calls for this to be acid catalyzed. So let's add in an acid, for example, H2SO4 is a good strong acid. You can think of other strong acids as well. This is a non-nucleophilic acid, so we don't have a group that's going to attack our epoxide, like if we used HCl, for example. And we are going to get this sort of intermediate situation where we're going to protonate our epoxide. We have 1 lone pair left, and then an H plus here. All right, I'm going to draw an overall HSO4 minus counterion because I don't want to draw it with every single structure that I'm about to look at here. Okay, so now we're thinking about, we have 2 places that our epoxide could ring open, all right? And last time we were very much guided by an SN2 mechanism. All right, so let's kind of take a look at some ways that we can think about this particular molecule, all right? So we're going to start to break the bonds between the carbon and the oxygen, all right? And if we start to break the bonds between the carbon and the oxygen on the more substituted side, what we're going to get is this partial bond that forms here. We still have our H. And instead of assigning the H, the plus entirely to the oxygen here, because we're starting to break this bond, I'm going to say that we have a delta plus at both of these positions. All right, delta plus at both positions. Right, it's almost like taking that positive charge we had on oxygen, dividing it by 2, and then assigning that there. Okay, so now let's take a look if we were to start to break the bond on the other side. So that means we keep our bond on the more substituted side to oxygen intact. But we start to have a partial bond between the less substituted carbon and the oxygen. And here again, we can sort of roughly divide our positive charge in half, and we can get a plus at both, delta plus at both positions. So partial positive charge at both positions. Make that easier to see. All right, so now we need to consider which of these is more stable. We're really taking a look at the stability of these two carbons. All right, and what we see is that a tertiary carbocation is much more stable than a secondary carbocation, right? So in this case, what we can say is this is more stable because it is tertiary. All right, that delta plus charge, the partial positive charge, is more stabilized at the tertiary almost carbocation that's forming. All right, and so that means the nucleophile attacks the tertiary position. All right, so this is the explanation for why we get the regiochemistry that we get. All right, so this is a more SN1-like mechanism. I'm not calling it a full SN1 mechanism because I have not drawn a total breaking of that CO bond. We're sort of living in between land here, all right? So it's an SN1-like mechanism. Okay, so now let's take a look at what this looks like with a nucleophile. Okay, so we're gonna have an epoxide. Let's, for example, say this is our tri-substituted epoxide. It looks like the one before, I just flipped it over. All right, let's add in a nucleophile on our acid. So in this case, let's add in methanol, all right? And we're gonna get basically like a methoxide that's been added. So we're gonna do this under H2SO4 or acidic conditions, and then we're gonna add in methanol as our nucleophile, all right? So the intermediate here, we're gonna go ahead and we're gonna protonate first. So we're gonna protonate, we're gonna break what at the end of the day is a HO bond, so I'm gonna give the electrons back to the oxygen, and that's gonna give us an intermediate that as we protonate, right, we start to break that bond that we talked about before on the more substituted side. So overall, this has a positive charge and the HSO4 counterion. HSO4 minus counterion, because we deprotonated, right? I'm not officially assigning that positive charge to any particular element, right? Because we are thinking about that charge being distributed as a delta plus on the oxygen, as a delta plus on the carbon. And it turns out as our nucleophile is attacking to break this bond, we start to see that this bond is starting to be made, this partial bond here. We start to see that also we have a delta plus on our oxygen here. All right, so we haven't talked too much about partial bonds, but this is what happens in this reaction, all right? So that's why we call this SN1-like. All right, it's not fully an SN1 mechanism. We haven't formed a full carbocation anywhere. We've now just distributed the positive charge over 3 elements. Okay, so let's take a look at what that product looks like of that reaction. So we already have our OH. We don't need to protonate it at the end, right? We protonated it at the beginning. We have our carbon at the unsubstituted, or the less substituted side. Great, everything looks good. And now we have our oxygen carbon bond from our methanol, and that is now where our positive charge comes from. HSO4 minus, right? Now that we've had that bond, that full bond actually made, we can assign the positive charge to our oxygen. All right. We'll just deprotonate using HSO4 or methanol is probably more acidic, so we'll just call this a proton transfer. You could, if you did it from methanol or from HSO4 minus, doesn't matter to me. We can get to our final product, which is our methoxide group that's now on our epoxide. All right, so here's the really tricky part, why I've been emphasizing it's SN1-like, not SN1 mechanism, SN1-like. So it's SN1-like because a full carbocation is not formed. Okay. Now here's the kind of crazy part, that inversion of stereochemistry still happens. So that argues for this being SN2-like as well, okay? So that's why it's a little bit confusing, but because we never break that bond fully to form a carbocation, we don't erase the memory of that stereochemistry through rehybridization. There's a lot going on here. So what we can think about doing is an example of an epoxide ring opening of a tri-substituted epoxide when we have stereochemistry. So let's take a look at what this would be. So we have our methyl group down. Right, and so if we were to do this with a nucleophile and an acid with a nucleophilic component counterion to it, like a bromide, we could go ahead and use the bromide to ring open this. We would get inversion of the stereochemistry, which means that on the side that's not being reacted, I would get my OH in the same stereochemistry, but on the side that is being reacted with, I'm going to go ahead and I'm going to get my methyl group coming towards us, and my bromide is going back. Right? So this is the stereo center that was inverted. So this is the tricky part. With SN1, we're like, oh, we can forget stereochemistry inversion rules. Well, this is not an SN1 mechanism, it's SN1-like. All right. So let's have our own learning objective on this because it's kind of a lot of information. All right. So our learning objective of 17L is to predict and explain the outcomes of nucleophilic addition to substituted epoxides. Right? And when we're talking about the outcomes, we're specifically saying regiochemistry, which is where we react, and stereochemistry, which has to do with our stereo centers. All right, so we're looking for both. Where does it attack and does it invert or not? Okay, so let's just talk through a couple of examples for this, okay? So say we have a tri-substituted epoxide. Okay, let's just count our carbons. 1, 2, 3, 4, 5 in this case. We have 5. All right, so now let's take a look at our reaction. What is our nucleophile? We can say that our nucleophile is methyllithium, for example. Okay, so we can take a look at our conditions and we can say methyllithium is a strong nucleophile. And if we have a strong nucleophile, that means an SN2 mechanism. We don't need to worry about these partial positive charge buildups. We have essentially what we're thinking about is methyl minus. So then we would say our mechanism is going to tell us that this is the sterically most accessible position. And we know a lot about SN2 mechanisms, that they go for the sterically most accessible position. And so we could say to ourselves, we are going to react at that carbon that is sterically most accessible. So we can number our carbons here. We're not going to change the stereo center between carbons 3 and 2. And we can, of course, add in our H3O plus at the end of this in a second step. So first we would get this as our lithium alkoxide that forms from that nucleophilic addition at the sterically most accessible site. We would add in our H3O plus in step 2. And then we would get out our neutral product. All right. So this is analogous to a lot of ethylene oxide ring openings that we had seen before, right? Sterically less accessible than we protonate. Okay, say we were given on an exam this particular epoxide. And we have a substitution pattern with a methyl group and an ethyl group on one side. And we have a methyl group on the other side. We have a tri-substituted epoxide. Okay, so our tri-substituted epoxides, now we really need to see what our nucleophile is. So if our nucleophile was sodium azide, for example, this is a strong nucleophile. So SN2. All right, so our SN2 site we would see is the less hindered one, right? Our SN2 site would be the less hindered one. Even though this is a tri-substituted epoxide, we have some special rules for those. Because we have a strong nucleophile in this situation, we are not worrying about the buildup of positive charge. And so if we were to add sodium azide to this, what we would end up with is substitution at the less hindered position. And we would have inversion of the stereo center. I'm just going to draw it as if we've also protonated it. All right, so we would have stereo center inversion. So that methyl group that's coming towards us is going to be inverted. All right, we're going to form our azide bond. All right, this side has stayed the same. This side has inverted. All right. So if we want to draw this, we can draw this in many different ways. We could do some bond rotations, however we wanted to depict that, all right? But we would see that that stereochemistry needed to be inverted. Okay, say we were given the scenario, though, where a nucleophile is not a strong nucleophile. Instead, we were given the conditions with methanol and H2SO4. We would say this is weak nucleophile, and so it's SN1-like. I'll draw my arrow longer so we don't run out of room. All right, so now we would come over here and we would say, okay, we have our more substituted position, and this is the SN1-like site of attack. Right, because it's that tri-substituted, and we see that the buildup of that partial positive charge would be more stabilized there. And the product that we would get out on the side of the molecule on the left is going to be the same. We're going to have an alcohol, and our methyl group is going to be the same. And on this side, we're going to have inversion of that stereocenter. So our ethyl group is going to be coming towards us. Our methyl group is going to be going behind. All right, and then our incoming nucleophile is in the plane of the board. Again, I highly recommend all of you flip these bonds around, see if the stereochemistry isn't looking good to you. For example, you could be able to line that up in a different situation. All right, let's go ahead and do a chime in question that kind of asks exactly what we're thinking about for learning objective 17L. We're going to have to analyze our nucleophile. We're going to have to analyze our substitution pattern as well. All right. I've opened the question on my phone, but for some reason on my iPad it's not looking great. So feel free to, it should be open. The question should be open, so you can go ahead and get started on that while I switch to this. Let's see here. All right. So, yeah, we're thinking about those conditions. We're thinking about the type of epoxide we're getting. We're thinking about the stereocenters. Let's see what people are thinking. So let's go ahead and take a look at where we're at here. Okay, view results. Okay, so we start to see a couple of different responses, and I think this has to do with, I like that both the responses people are thinking about the substitution pattern. So we're going to add an epoxide here, and so for both B and C, we've added the epoxide and we've done some inversion of stereochemistry. So I'm going to draw this one out because it's a little bit hard to see. And after everyone sort of answers in. So yeah, you can submit your answers. I'll keep it open for a little bit longer, but I can't much longer explain. So. All right, so our chime-in question is asking us the following. If we have this particular epoxide, our stereochemistry of our benzyl group is coming towards us. And if we had ethanol and H2SO4, what would we get as our product? Okay, so we would be thinking we have two possible sites of reactivity. Okay, so we would be asking ourselves, if this is an SN2 mechanism, this would be our SN2 site, our less hindered site. If this was an SN1-like mechanism, then our site would be at the more substituted position. Okay, so now we can go ahead and evaluate, and we can see that our conditions are under acid. So we need to be thinking about the stabilization of a partial positive charge, which means that we would be breaking our bond at the SN1-like center, and that's where we would be adding our nucleophile, our epoxide. And because we're not reacting at the side that has stereochemistry associated with it, we can go ahead and leave that stereocenter intact, all right? And that's the correct answer. Okay, just for the exercise of this, let's go ahead and, sort of label these. This is our weak nucleophile. It's not deprotonated. We have acid, so we're going to have an SN1-like mechanism. All right. And this product would stabilize the delta plus charge best at tertiary center. Okay, so just because we're learning about this concept, this is the answer to the chime-in question is on this side, but let's just go through the exercise that if our nucleophile instead was sodium ethoxide, what product would we get there? Well, we would be thinking sodium ethoxide is a strong nucleophile. So we need to be thinking about an SN2-like mechanism or an SN2 mechanism with our strong nucleophile. All right. So that means at the end of the day, we would open up on the side with our stereochemistry inverted. All right. So what that would look like is our phenyl group or our benzyl group is going to be inverted, and now we've bound our ethoxide. All right, so we have both a different regioselectivity, meaning where our bond is made, as well as our stereochemistry. All right, so let's get to our final learning objective, which is to kind of put this all together, all right? So we'd like you to be able to do a learning objective of design a multi-step synthesis. Whenever you have this as a learning objective, it starts this way: design a multi-step synthesis. You know exactly on the exam which question this is going to be, which is on the final page, right? We ask you to design multi-step synthesis. So these are always the ones to study a little bit regarding that. So design a multi-step synthesis using the reaction of ethers. Right, so ethers have 2 carbons bound to our oxygen, so epoxides are, of course, a subset of ethers, okay? So if on an exam you were given this question with multiple arrows to go ahead and design to get to this particular product, let's see what you would come up with. We can say this is a racemic mixture. So we're just worried about the relative stereochemistry. We're not saying that we need to get a single number. All right, so if I was thinking about this, I would notice that this cyanide group here, you know, we'd seen that cyanide as a nucleophile before. So that's my hint to you to take a few moments and come up with what you think the retrosynthesis of this would be. How are we going to get here? What's the step before we get to this position or to this molecule with the cyano and oxygen in the vicinal positions? I think a pretty good place to start might be what we've just been talking about, which is our epoxides. All right. Seems like a pretty good way to get there. And then we could add in our CN minus. Obviously, we need to think about the actual reagents, which have to have a counter ion to it, but that's just how we're going to get there. Okay. And then we also need to think about the fact that we can get to our epoxide from an alkene, right? So this is actually a multi-step synthesis that just is going to require 2 steps. So let's talk about the forward direction. Okay, we started out with an alkene. We know you can do an epoxidation with MCPBA. So that seems like a pretty good way to get to our epoxide. Okay, and now we know we have these opportunity to have a cyanide nucleophile. We don't need to worry about which side to react with. It'll react with both. So we could use something like sodium cyanide. as well as H3O plus workup. And we would get to our final product. All right, let's do, I'll let you copy that down. Yep, question. Yeah, so I'll repeat that for everyone. On an exam, do you have to pick an acid for the workup step? No, H3O plus is great. I would say, generally speaking, we use whatever is around in the lab. So oftentimes it's saturated ammonium chloride solution or 1 molar HCl or something like that. So it's really more of what's laying around. All right, let's talk about, this is a learning objective for ethers. So let's go ahead and recall some of our ether chemistry. So we just dealt with an ether, of course, that is an epoxide, but what if we have an ether that is not there? We want to turn it into something. Say we want to turn it into this compound here, a thioether. How would we get there? All right, this is recalling some of the things we've learned over the last couple of classes. Okay, so this ether with our isopropyl group, and now we have a sulfur. I think a pretty great way to get here would be to start from an alkyl bromide, and our learning objective said that we could use deprotonated sulfur reagents to be able to do SN2 reactions to make thioethers. Well, how would we get to our alkyl bromide? Well, we know we can get to our alkyl bromide from our ether, right? And a bit of HBr acid. So let's see what this looks like in the forward direction. Okay, so we take our ether. We don't need to worry. This is a primary ether on both sides. We would add in our HBr. We would get 2 equivalents out of our HBr bromide and our water byproduct. Then we would add in our nucleophile, which is a sodium phenyl sulfide, and then we would get to our final product. All right, so this is what we're thinking of you all to look for, is just where can we break bonds and how can we go backwards. All right, that's all for today.